This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you the final condition of my motorized microscope. So in the previous video I showed you that I assembled the circuit to control the microscope, and I showed you the basic principles of it and how it operates, but not everything was finished in a way I wanted to. So now everything is finished, so I can show you how it works and I can demonstrate the capabilities of this system. So just a little refresher, we have a optical microscope here. It has 4 lenses, and now as you can see it has a motorized XY stage, but in addition to that the Z axis is also motorized. I will show you how it is motorized when I move the camera there. And on the top of this microscope there is an extension tube, and on top of that there is a mirrorless camera which through an HDMI cable transfers the image on that big monitor. So this whole thing is sitting on a cart, and then I just use the monitor arm to have the monitor floating above everything. So it's a very convenient arrangement. And then here we have a box which adjusts the brightness of the light, which is the light source for the microscope itself. So basically the illumination. And yeah, it's just a halogen light inside this part, and that illuminates the surface of the specimen that we are inspecting. And then under that there is a more important box, and I will show you it inside out when we move closer to it. But that's basically the controller there. So it has a display which can be used to display all the relevant information regarding the position of the stage, the condition of the stage, whether we are homing, moving, or the system is in a standby status, and so on and so on. It has 3 buttons, a moving forward and moving backward button, plus a abort or stop button. It has 2 switches because you can select between the modes, like joystick mode, button mode, and you can even control this thing via USB, so you can select that. And then when you are in a button mode, and since we only have 2 buttons, you have to pick a axis, so you can control 1 axis at a time. And then with the help of the selector switch, we can say that we try to move the X, Y, or Z axis, and then the buttons just move the selected axis. And there is even a status LED. You will see it better when I move closer to the front panel. And that LED, similarly to the display, tells the user what is happening. So there are different colors because it's an RGB LED, and there are different behavior, let's say solid light or blinking light, and that will tell us what is happening to the system. And finally, we have a joystick. It's a 3-axis joystick, so it can move left and right, up and down, and then I can even twist the joystick, which actually moves the Z-axis. And the joystick is connected, and the system is programmed in a way that the movement of the joystick is replicated by the stage. So if I move the joystick towards the left, then the stage moves along the left direction or left way, and so on and so on. So let's move closer to the box and see what is there. So as I said, we have the 3 buttons. So this will be the forward button, the abort button, and the backward button, or positive and negative direction or action. And then this is like stopping, or it also acts as the homing button. And then this is the status LED, and then this is the mode selection. So when it's in the up position, it's joystick, and then when it's in the center position, if it's then it's button controlled, and then when it's in the bottom position, then it's USB controlled. And then similarly to the previous switch, we have 3 positions here. So the top position is X axis when we are in a button mode. When we are in the button mode, the middle position is the Y axis, and when I push it to the bottom position, then obviously we have the Z axis left. Then here we have the joystick. So as I said, it can move left and right, up and down, and then I can twist it both directions, and that will move the Z-axis. And this is a 3D printed part. So I just designed something quickly in Fusion 360, and then yeah, I printed it. So then this is the stage, and the stage is a planar stage, let's call it like that. So it moves in the XY plane. So under this cover there is a lead screw that moves the axis on the X direction, and then under this part of the stage there is another lead screw which moves the stage in the Y direction, and the motor is down here. And then there is another 3D printed part here, which is just this disc. So I printed this because, as you can see, there is a hole here, because the stage originally had some kind of insert like this, but I don't have it. So I just measured the things and printed this. And why it has a slot there is because this slot precisely fits the glass slides that I'm using to glue my transistors and other components on it for inspection. So then I can put the slide on it and then just put it there. And then I also set up the stage and the box in a way that when I home the system, then this is actually the home position. Because when it moves to the limit switches, then of course the system moves to the extremes and parks there according to the, let's say, default behavior. But then I make the system park in the center. So I actually marked the center of this insert, and I measured the position of it, like the real world position in millimeters. And then I set up the homing in a way that it will actually move to that position. And the Z-axis doesn't care about this, so it will just move up, and then it will do the homing, and it will stay 5 millimeters below that position. But we don't care about that much, as we care about the center position on the XY axis. So now we are looking at the Z-axis mechanism. So this is the default knob of the microscope, and this moves the Z-axis up and down, as you can see it. But then I made an attachment here with a stepper motor, which actually moves this knob. And I showed this already in a previous video, so check that if you are interested in it. But basically we have a normal NEMA 17 stepper motor up here. It is sitting in a 3D printed bracket. And then there is a GT2 belt here, some simple tensioner here, and then there is a knob here as well. And behind that knob there is a pulley wheel. And this wheel up here has 20 teeth, and this down here has 60. So we have a 1:3 gear ratio. So while this rotates one full turn, then this only does 1/3 of a turn. So this has to be turned 3 times to make a full turn on this. And actually I will move all the 3 stages, and I will show you that they move according to the calculations and according to the values that I'm displaying on the display of the controller. So now we are looking at the controller. So let me turn on this thing, and then let's see what is on the display. So now, as you can see, we have several different information on the display, and the display is, let's say, split into 2 parts. So this is actually a very simple LCD. This is, if you Google 2004 LCD, then this is the product, but you can check it on my website as well. I could have picked a fancier display, yes, maybe a smaller one or something, but why I picked this is that it's easily available, easy to program it, and it's easy to look at it because it has large characters, and it also has very good background light. So I actually like to look at this, and it kind of matches the rest of the, let's say, design of this unit. So what we see here actually is the following. So we have X, Y, and Z positions, and now they are all at 0 because I haven't performed the homing yet. And then you can see that the system is in standby mode, and that is also reflected by the blue LED there. So when the system is in standby mode, so if it's not moving and everything is normal, and then the system is in standby mode. And then I kind of tried to separate with these vertical lines the display to two parts. So on the other part we have like two information. One is the mode, and now we are in joystick mode, so I could control the stage with the joystick. And then the selected axis is Z. So if we are in the button mode, then the actual axis, which will move when we press either this button or this button, it will be the Z axis then. So I just want to show you first these two switches, how they behave and how they operate. So as I said, we have two switches, this guy and this guy. So this switches between the modes, and this switches between the axes. So let's just switch through the axis, just so I can show you how it behaves. So I flip this switch to the middle position, which should switch the axis to Y. So now if we are in a button mode, then the Y-axis is active, and then this is X-axis. And then if I change this, now we are in joystick mode, but if I go down, then it becomes button mode, as you can see. And if I go down, it will be USB mode, because this can be controlled by USB commands through the serial port. So that's what we have there. So I move back to joystick mode, and then I just show you that I can move the stage with this. So now I tried to align the camera in a way that it shows both the stage and the joystick. So I just show you how it works. So I move to the right, then the joystick moves to the right. And of course the joystick is also regulating the speed. So if I just move a little bit, then it should move a little bit. But I just bring an object here because everything is kind of dark colored, so it's hard to find a reference spot. So we have a friendly duck here. So let's make the duck travel to the right and to the left. Now it can go backwards and towards me. And if I put the duck here, then I can make it disappear to some extent. So all the axes move. I can switch to button mode. And then now the X-axis is selected. So let's put the duck back. And this will be the positive direction. So it moves that way, away from the motor. And then this is backwards. And then I can go to Y-axis. Now the duck is coming towards me because that is, again, away from the driving motor, which is back there. And then this goes back. And then let's put the duck back here and switch to Z. So now the duck comes down, or alternatively I can drive it up as well. So this is all nice, but you could see that, for example, when I was in the button mode, the duck was moving, or the axes were moving quite slowly. I actually made a solution for that. So if I go back to joystick mode and select a certain axis, and then I press the forward button, then actually that will apply a speed multiplier. So for example, if I do it in the Z axis, then that will be 5 times the, let's say, default speed that I stored in the code. So let's do it. So this is supposed to store it. So I go back to button mode. And then now we can check it if it works. So this is the z-axis, so it's not so spectacular. So I go to x-axis. So now it works fast. The z-axis has different multipliers because the z has to move very finely, especially when I try to focus. But now you can see that, and you can listen to it, how fast it moves. It has a different pitch. So I go back to joystick mode again. And now we are at the x-axis, so I press the forward. And this should turn the speed back to a kind of slow mode. And you can see that now it's slower. And of course there is a middle position. So back to joystick mode, I go to the y-axis, press the forward. Then I go back to button mode. And let's test it. I stayed at y-axis, but doesn't matter, it's the same speed. Y-axis and x-axis have the same speed. But you can see that this is kind of faster. And just to show, so joystick mode, z-axis, which corresponds to the fastest speed, and press the forward button. Then I go to button mode, y-axis, this should be fast. So that's that. But now, actually, hopefully you can see, kind of, on the display that we have very different numbers here. And that position is actually not really calibrated, or they are not well-informed positions per se, because we don't know in compared to what that is 10 millimeters or 7 millimeters or something, because there was no homing. So what I do now, I press the middle button, which is not visible, but this black button there at the very right side of the picture, or maybe so that button, and that will initiate a homing. So let's do that. So the homing is completed, and as you can see, yeah, nearly everything is at the 0 position. Sometimes I get some garbage number here, which I will fix, but the basic reason for that is that when I do certain divisions to convert the number of steps into millimeters, then there might be some rounding errors. And because of that calculation, sometimes I can end up with those numbers, but that is basically 2 micrometers. So does it really matter? Probably not, because we are observing 1,000 times more sizes. So I just basically don't care. But if I wanted to, I could make that 0 perfectly as well. So now we are at the home position. So I want to show you that those numbers actually don't lie. So I have a dial gauge, and I will fix it to the 3 axis, and then we will move everything and see how precisely we can move to a certain position. So I set that thing up now. Okay, so we have everything arranged here now. As you can see here, we have some metallic plate here. This is one of my old metallic plates for my DIY tensile testing machines. And the reason why I have it here, because the arm, the holder, this thing here, for the dial gauge is magnetic. If I would not use the metal plate under it, then it would slide away because of the spring inside this needle. So I needed some magnetic thing under it, and yeah, that's what we have here. And then I tried to carefully align this flat. So first everything was made sure by this water level here that I aligned it flat and then I slightly tilted the display. Then it just rotates in the socket, so it should be still in level. So the needle will move parallel with the stage, hopefully. And then I align the camera that we see both displays very well, hopefully. So everything is in the correct mode. So x-axis is selected, and that's what we are measuring. And button mode is selected. So let's move with the button and let's see how these two numbers align. Oh, and while I press the button, observe the color of the LED. So what we have here is 9.82 and here is 9.863. So close enough. And if I move backwards, uh, 0.02 minus 0.02, both of them started from 0. So there is this should be also negative. So there is a small discrepancy there. So let's move again. So 9.61, 9.57. That is also close enough because, yeah, 61 minus, or let's call it 62 because the last digit is 9. So 62 minus 57, that should be 5. So 0.05 millimeters or 50 micrometers difference. So the principles in the box is just using the number of steps from the motor and the pitch of the lead screw that moves the stage. So that's a pure mathematical formula. And then this one is whatever equipment, but we don't know its accuracy. Despite these unknown things, the discrepancy between these two things is just 50 micron. 50 micron is the thickness of a human hair. So I don't really care about that difference. So we get reasonably good numbers on the display. That's what I'm trying to say here. So it's moving as it should. And now I see the negative number here. I was wrong because yeah, we are always moving on the negative scale. So actually that 0.02 was correct, or 0.2 on both sides. So it was kind of something like this. But yeah, you can see. Because when this turns positive, then that's negative. So I was wrong, but the system was correct. But you can see that it moves correctly. So 45, 49, yeah, it is what it is. I still accept that difference because again, it's let's say 40 micrometers, again, human hair order of magnitude. So the x-axis moves with this kind of tolerances and precision, and the y-axis is exactly the same lead screw, the same backlash correction or anti-backlash nut, and same bearings. So I would not test that because it would be the same results, hopefully. But the z-axis is more interesting. So let's check the z-axis. So I could not put both of these displays in focus, but the digits are large enough here on the dial gauge that they will be still visible despite the fact that it's a bit blurry. But what is more important, I think, is on this display. So I select the z-axis and I'm still in button mode. So now I just move in the positive direction and see what happens. So you can see that the numbers and both the numbers and the z-axis move down. So I just stop right here. So this is easier to read for me. Minus 643, positive 6733. So there is a little discrepancy, 300 microns, but it's not too bad. And also the problem could be that I attached this to a quite wonky position. So you can see that now it's 52. So trust me that this is good enough, let's say accuracy, but let's move a bit backwards. So I move back close to 0, just so I can zero this. And you can see that actually this is such a silly design that you have to press the button with such a strong force that you can actually move the whole thing, and then it will never tear at 0. So you can see that it's a bit silly device. But yeah, it's hard to fix. So now I fixed it at a different place, and remember that the last digit here is 7, the third digit. So now I move. So 5005 on the dial gauge and 5085 on this. So by just rearranging this, and still it's a wonky setup, I could improve the number of digits here in a sense that, yeah, it's better because this thing can move better. So now the discrepancy is basically 30 microns or even a bit less, which is again in the order of magnitude of the human hair thickness. So I kind of accept that. So now I want to go inside this box and just show you how everything is connected and how it looks like, so you can understand the principles of the electronics behind this machine. So this is the inside of the box, and you could be already familiar with this thing because I showed this in a previous video, but I just want to go through what kind of modifications we have here and how things look like. So just briefly about the circuits used in this printed circuit board. So we have a TNC 4.0 microcontroller that controls everything, basically. It's a high-speed, high-performance microcontroller, so I really like to use it in this project. And then we have a TMC 429 ramp generator. It can control 3 independent stepper motors, and it can generate the step and direction signals for it. And its advantage is that it unloads the TNC, basically, or any microcontroller that you use. Because how it works is that the microcontroller sends out a serial message to this device here, to the TMC 429, and then that's that. And then the device here just does its job and sends out the signal to the 3 individual TMC 2209 stepper motor drivers. Because if you use, let's say, the Access stepper library and you drive a stepper motor, then you have to toggle the pins of your microcontroller, which takes CPU time and it blocks the CPU. But here you don't have that issue because the only time when you block the CPU, and that is just a very short, brief period of time, is when you send out the message on the SPI to the TMC 429. So that's that. And then, yeah, we have the TMC drivers. I already mentioned them. Here I have a GPIO expander because I have the switches and the buttons that I need to take care of. So I actually use this expander to poll these switches so I can see if something changed in their status. And the polling is enough here. I don't need interrupts. And then you can see this cable. Originally there was a RGB LED here, but then I just bring those 4 connections to the front panel. So then the RGB LED is also in the front of the enclosure. And the PCB also has a dedicated I2C connector here, so that then allows us to connect this I2C display. And there is an onboard voltage regulator here, so that just provides 3.3 volt voltage to everything except the TNC, because The device is also compatible with PC communication, so I wrote the software for this in a way that the user can send commands to it. So in that case, I found a bit difficult to separate the power supplies. So what I do here is that I just say, okay, everything except the Teensy is powered from the external power supply. And then the Teensy has to be powered by its own supply. So we have a 12-volt adapter for most of the circuit except the Teensy. If I use it in a standalone mode, like in this video during the demonstration, then that is just powered from a wall adapter as well, a simple USB phone charger. So then that is basically what is inside this box. And if you want to have this PCB, which I use to build this project, then go to my project page on PCBWay's website, because then there you can find this project. I wrote a very detailed description, and then you can see what kind of hardware you need, how you can assemble it, and what are the features of this board. And you can either have the bare boards, or you can use PCBWay's assembly services, and they can deliver you an assembled board. So head over to PCBWay's website and check my project and their services. So now I think this demo is finished here with the hardware. So let's take a look at a few microchips and stuff like that under the microscope. So I can explain you how I move the stage and so on, so we can see how smoothly I can navigate and how that looks like when it's recorded with a camera. So let's move back to the microscope. So now I put a chip under the microscope and it's out of focus because the Z-axis is high. The system right now is in joystick mode, so I will just twist the joystick to bring the objective closer to the surface of the specimen, so we focus. And I try to move it slowly, so you will see as the object becomes more and more focused. And I went a bit beyond. There we go. So this is the surface of the chip. So you could see that I could focus it more or less easily with the joystick. But actually I made the slow mode of the button exactly for this. So let me select that. So now I'm in button mode and hopefully the slowest mode is activated. And I'm moving on the Z-axis, so let's see how the system behaves. So we go out of focus. And now it's more or less focused. So you can see that with the button it's even easier. And I could set the button to an even slower speed when it's at the slowest setting. So then I could have it at a more finer step size. So now I'm getting out of focus. And I'm approaching the focus again. So it's somewhere here. I go back to joystick mode. And I try to navigate on the X and Y axis. So this is a bit choppy, but it kind of works. So for rough navigation, I guess the joystick is enough, as you can see. It's also my hand or the mechanism on the joystick that it's just hard to keep it at one speed. So therefore it doesn't move well. But if I go to button mode and I go to the X-axis, then let's see what happens. That was a bit too fast. So I change the speed. So now Yes, this is way too fast even at the slowest setting. But this is just tuning it, nothing else. But you can see that it moves very smooth. It's just too fast. So I could not, let's say, record a panning video with this yet. But yeah, it takes me 2 minutes to reprogram this thing. So yeah, it works. So I'm satisfied with this, and all the features of the circuit and the software works fine. So I consider this project finished. So if you want to build your own controller, then head over to my PCBWay project site. You can get the PCB manufactured by PCBWay, and then you can build your own circuit and then program it as you wish. And if you are interested in similar projects in the future, you can become my Patreon supporter. And just as a side note, I haven't published this software that I'm using on the microcontroller, and I'm not planning it. Some people were complaining about this, but this is a lot of work and it's my own intellectual property, and I decide what I do with it. So if I don't want to publish it or don't want to put it on my Patreon, then it's my decision. So for example, if you purchase the PCB and you hope for a software, or you become my supporter on Patreon and hope for a software for this project, you will not find it. So keep this in mind. This project is more for showing my skills and knowledge and sharing ideas with you regarding this kind of topic. So I hope you liked this video. I hope you learned something, and see you in the next video.